Okay, so I'll copy this over. We'll start off with a clicker question. And it just says, imagine we have a linear regression model. The scatter plot shows that a linear relationship is appropriate, and the best fit line has the equation height hat is equal to 1.25 plus 0.45 times days, where x represents the days since being planted and y is the height of the plant. And the question that you have to answer is, what is the interpretation of the slope? Okay, and so these are your different answer choices. And some of these sound sort of correct, but only one of them is actually correct. Let me get our clicker session started. Okay. So I'm hoping your clickers are working. And if you want to talk to your neighbor about the answer, you are welcome to do so. So you can talk to your neighbor about what you think the answer is. So, okay, so I'll let that run. I'm gonna pause the video here. So we'll click stop. 3, 2, 1. Okay, let's take a look. And that is correct. C is the correct answer. Okay, so why is A not correct? All right. The key here is that it seems to indicate that the height, okay? To make A correct, so A is not correct, but to make answer choice A correct, so A is almost correct, but to make answer A correct, we would need to say the predicted height. Okay, if we write the predicted height increases, predicted height increases by 0.45 centimeters for each day that passes, or the expected height increases, that is fine. So if you included the word predicted height or expected height, then answer choice A would be correct. But because it does not have that in there, then it seems to indicate that the actual value of height increases for each day that passes, and that's not true, okay? The linear regression model is just a model showing what we predict or expect to happen based on the x value. And so answer choice C is correct, and it sounds a little bit funny to say if we increase the number of days since planting by 1, but basically what we're saying is if we increase x, if we increase the x variable by 1, which x is days since planting, so if we increase the number of days since planting by 1, we expect the height to go up by 0.45 centimeters, which is the interpretation of the slope here. Okay, so that is what we have. Are there any questions or objections here? Okay, then we'll continue on. And so I believe on Wednesday we left off, we discussed the interpretation of the slope, but we had not yet discussed the interpretation of the intercept. Okay, so the intercept is A, okay? We have y hat is equal to A plus B times x. The intercept is A, and the intercept, that value A, is our prediction for y if we plug in 0 for x. So on the previous slide, let me just kind of copy our equation. Or I got height hat. Oh my goodness, I'm so sorry. It says it's muted. What are you? What is this nonsense here? Okay. The interpret that threw me off here. Okay, so we've got, predicted height is equal to 1.25 plus 0.45 times days. So in this case, 1.25, this is our intercept. Okay, so our intercept is 1.25, and that means if we plug in 0 for days, we predict height to be 1.25. So here we're talking about, I don't know, I guess like plants. We've planted little seedlings. And so what we're saying is that, what this linear model shows is that, when you plant it, each day that passes, the seedling grows about half a centimeter, okay, 0.45 centimeters. And what we're saying is that if we just planted it and we didn't let any time pass, then the height of our seedling we would expect to be 1.25 centimeters. Okay, so another word is if no days have passed since planting, okay, we expect the height of our plant to be 1.25 centimeters. Okay. We should note that sometimes it does not make sense to plug in 0 for x. Okay, and in those cases, there's no practical interpretation for the intercept. Okay, so here's another example. Let's say we're talking about snake length and snake weight. So x is our snake length, y is our snake weight. All right, and I'm just going to make something up here. So we'll say y hat is equal to, I don't know, 21.4 plus 15.1 times length. All right, so in our case, our intercept is 21.4, and the direct interpretation is if we have length equal to 0, we predict the weight to be 21.4, I don't know, whatever we're talking about, grams or something like that. Okay, but you cannot have length equal to 0. Okay, it is not possible to have length equal to 0. So a snake with length 0 is literally no snake. So it doesn't make sense. Okay, so it is not possible to have length equal to 0. And so the intercept does not have a meaningful interpretation or meaningful interpretation here. So in certain cases, the intercept does have a meaningful interpretation. In other cases, it does not. Let me talk a little bit more about kind of some of the conceptual ideas behind linear regression. Okay. We can think of linear regression as the model is trying to model the relationship between x and kind of the average or expected value of y for that x. Okay, so linear regression tries to model the relationship between x and the average value of y for that x. Okay, so you can imagine. Let's draw a scatter plot here. All right, and let's say I've got we've got a some amount of we'll say we've got a decent amount of scatter here. And what we want to do is we want to create a relationship between x and y. Yeah? And so you can imagine for a particular x, I can take a, let's say, for this x, I'm going to take kind of just a slice of the data here, okay? And so inside this slice of the data, right here around x, I've got a few data points in here. Okay? So just for this slice, I've got, looks like in my picture, I've got about 5 dots there. And we can say, all right, well, I want to know what is the average value of my data for this particular x value. And I would probably say, okay, well, the average of these 5 dots, maybe I'm going to draw a little triangle there. And that would be kind of the average value of x right there. Okay, over here, I can come over here and here's another x, and I'll draw a slice of data. Take a slice here, and here it looks like I've got 1, maybe 4 data points in this little slice here. And so what I would do is I would say, okay, well, what's the average of these 4? And so looking at kind of where the middle of these 4 would be, I would say that's kind of the average. And we can imagine taking slices of data for different values of x and trying to find the average of those things. And so what linear regression is attempting to do is it's trying to find the relationship that models this where the averages line up. Okay, and so if we were to draw kind of just another x value, and take a slice here, of these data points, yeah, maybe the slice is right there. Okay, so that's what linear regression is trying to do. This line, the best fit line here, represents what we expect the average y value to be for a particular x. So you can imagine, for this particular x value, what do we expect the average y to be? We expect it to be here at this line. Of course, any actual value of x could be larger or smaller than that. And so the linear regression line is not trying to model individuals, but kind of the average average value of y for a particular value of x. So the line is not trying to model individual values. But rather the expected value of y. Expected, value of y for a particular x. Okay. And what do we call the difference between the expected or predicted value and the actual value? It's called the residual, right? So the residual, so pretty much every observation, the residual is the difference between the actual and the predicted value. And that's fine. You're going to encounter residuals in linear regression. So far, so good? Yeah, great. I know it's 4:20 on a Friday, so let's okay. The order of variables, okay. Order of variables matters in linear regression, okay. So which variable you call x and which variable you call y matters. Okay, so in one scenario we could say x is snake length and y is snake weight. And in this scenario we use x, we use the length to make a prediction for y. Okay. So this is like you have a this silly scenario would be you have a ruler or you have a measuring tape. You have measuring tape but no scale. And so maybe you create y hat is equal to a plus b times x. B is equal to r times the standard deviation of y divided by the standard deviation of x. In our case, r is the correlation. Standard deviation of y is standard deviation of weight divided by standard deviation of length. So you do, I don't know, something like this. Okay, and then you get some more. Okay. If you wanted to switch these around, that's fine. Okay, we could swap them around. We can, if we want to call x snake weight and y snake length, that's fine. Okay. But the scenario is now different. Now we use weight to predict length. So this time it's like we have a scale but no measuring tape. Okay, so here we have a scale but no measuring tape. And the important thing here is do not just take this equation and try to solve for x in terms of y, okay? Do not take the old regression equation and try to solve for x in terms of y. That will give you the wrong answer. What you need to do is you must recalculate the slope based on the equations and intercept accordingly. You must recalculate the values. So in this case, our slope here would be b is r times sy divided by sx, but sy this time is length. So this would be r times snake length divided by standard deviation of the weight. Okay, r times standard deviation of length divided by standard deviation of weight. So you would get different slopes. If you just took the tried to solve for one over the other, you'd get 1 over this thing, which is different from what you have over here. All right. So don't, when you swap the variables, it changes the meaning of what you're predicting, and you cannot just solve for one in terms of the other. You have to do, you have to recalculate everything. Okay, let me give you some warnings about linear regression. Actually, I need to see the time here. Warnings. Okay, because linear regression and regression in general is a very powerful tool. You're able to make numeric predictions based on certain inputs and things like that. Statisticians, we love to use it, but if you're not careful with it, could get you into trouble. Okay, so number one is just because a linear regression exists does not mean that there's a cause and effect relationship. And I know I said this before, but it's worth noting again. Does not mean so, I just read today some study came out on like diet soda consumption, and I don't know if they did linear regression. They probably did not. I imagine it was something else. Okay, but maybe. Okay, and basically the article said people who drank lots of diet soda had a higher risk of stroke than people who did not drink diet soda every day. Okay, so that they said like there were people who drank diet soda every day, their risk of stroke was like 3 times higher than those who drank it like less than once a week. Okay, that relationship might exist in the data. Does that mean drinking diet soda is what is causing the stroke risk? And the answer is no. We don't know. Okay, there could be people who choose to drink diet soda may have other there might be something in common about these people who choose to drink diet soda that puts them at a natural risk for stroke or something like that. Okay, we don't know. People who choose not to drink diet soda, there might be something in common about these people that puts them at a lower risk for stroke. Okay, there's all sorts of other stuff going on, and just because linear regression relationship exists, I'm sorry, I should say just because a linear relationship exists does not mean a cause and effect relationship exists. Sorry. Okay. Another thing is we have to watch out for outliers. Okay, so be careful of outliers. Okay, so let's say we measured people's shoe size and annual salary. Okay, so we say, how big are your feet? And we put them all on the same scale, okay? Because so we said, how big are your feet, and how much money do you make, okay? And what should we see? We should see pretty much no relationship, right? Actually, but I was thinking about this, and I was like, we'll probably see some kind of relationship actually because of gender wage gap issues, but we'll pretend like all is well in the world and shoe size and annual salary has no relationship as the way it should be. Okay. Now let's say somehow Shaquille O'Neal was in your data set. Okay. So Shaquille O'Neal, he's, if you don't know, basketball superstar, very, very big feet, and he makes a lot of money, okay? I mean, he made a lot of money as a basketball player. He's like this entrepreneur. He's on TV. He's a TNT basketball commentator. I like him. But okay, so he owns like a bunch of Five Guys franchises or something. Okay, I don't know. All right, okay. So Shaquille O'Neal, he would be like somewhere out here, okay? He has huge feet, lots of money, okay? So, this is check. And so if you included him in your data set, suddenly, so this is what it should be. There should be no relationship. There should be no relationship between shoe size and annual salary, although that's not exactly a flat line. This is what it should be, and with Shaquille, now suddenly you've got this going on, right? So this messes up our analysis, and if we include Shaq, then if we include the outlier, it might appear that bigger feet means larger salary, okay, or is associated with larger salary. If we include the outlier, it may appear that there's positive slope. So in this case, we would probably say, we're honored that you participated in our Study Shack, but for the sake of normal people, we're going to exclude you. Okay. And that's just the case with outliers. You shouldn't just delete outliers just because they're inconvenient, but in certain cases, it might make sense to remove them and make a note of it. Okay, other warnings that we have. Do not extrapolate. Okay, so extrapolation is the idea that you've collected data for a certain region and you continue the trend into areas where you have not collected data. Okay, so extrapolation is continuing the trend, or continuing the trend or linear regression into areas where you have not collected data. All right. So, just a silly example. Okay, so let's say you are the parent of a child at some point, or somebody is a parent of a child, and this person is very excited and measures the height of their child, every month. Okay, starting at age 2, every month we measure the height of the child, and every month the kid gets taller and taller and taller. Okay, and this has taken place every month for the past, we'll say, 10 years, okay? So we're at age 12. The kid has grown so much between age 2 and age 12. And we look at this, it looks like linear relationship. We fit a linear model, and it looks great, okay? Extrapolation would be to take that linear model and then continue it, okay, on forever, and then we would go, oh, wow, look at this. When the kid is 40 years old, or when this person grows up to be 40, you know, this person will be 20 feet tall, and then by age 80, this person will be 80 feet tall. We better let people know so that they can make accommodations. That would not be, you know, that would be a silly thing to do, right? Because we know, so, you know, we have data up to here. So this is, you know, data collected here in this region. Okay, and then over here we have no data. So in the region where you have no data, you cannot expect for the trend to continue. Okay, and so we know that for human height, it goes something like this, right? Like you keep growing until, I don't know, 15, 16, 18, 20, something like that, but then it levels off. Okay, but a lot of times different people will say like, oh, you know what, this you know, we've got this trend going on. This is where, you know, every year for the past 15 years this has happened, okay? Every single year. Look at this, okay? Every single year this is what's happened. So therefore this is what we think is going to happen over the next 15 years. But the truth is nobody knows what happens in the future, okay? You know, it could, as far as the future goes, any of these trajectories are possible, right? So no one knows what happens in the future. Lesson of the day. And so even though something has held true for the past however many years, 10 years, 20 years or something, it may or may not necessarily hold true for the future, right? So there's like Moore's law, which is like for the computers, like every, I don't know, however many years, the number of computations we can perform doubles and stuff. And it seems like it's held true, like for the past, somebody applied it all the way to like adding machines, and it looks like it's held true for 100 years, okay? It may continue to hold true, it may not. We have no idea, okay? And so to try to predict the future, that's not a good thing. Okay, so extrapolation, don't do that. What you are allowed to do, so you might say like, well, why did we even bother with linear regression if I can't tell the future? Well, with linear regression, what it's good for is areas where you have collected data. You can, you know, you can interpolate. Okay, so let's say like this person missed a month in terms of measuring their child's height. Okay, well, we can use linear regression to kind of get a missing value. Okay, we can interpolate values within the area where we have collected data. Okay, so we are allowed to interpolate. Which is, you know, use regression to, you know, make predictions in regions where we do have data. But if that, you know, then again, you have to be careful, okay? Don't take Shaq and then try to interpolate, you know, this missing region here. Okay, this is not a good idea. But you know, if you got a lot of data in a certain region, and you know, maybe one window you don't, interpolation is okay. Extrapolation, never a good idea. Excuse me. Okay. And then we have one last thing. This is not a warning, but this is just a final kind of concept, and this is the r squared value. Okay. R squared, this is known as our coefficient of determination. Okay, and for linear regression, and this is not, if you have more complicated regression, this is not the case, but for linear regression, our coefficient of determination, r squared, is equal to the correlation coefficient squared. Okay, so if correlation is equal to 0.7, then r squared is equal to 0.7 squared, 0.49. Yeah. So, okay, so why would we even bother squaring this and whatnot? Okay. The coefficient of determination, okay, r squared, tells us the amount of variation in y that is explained by x, the amount of variation in y that is explained by x. Okay, so let's say you wanted to find, x is the height. So let's say we wanted to say, is there a relationship between, we'll look at women's heights and their mother's heights. Okay, so we're going to say based on how tall a mother is, we'll look at the height of the adult mother and height of the adult woman. Okay, and we'll say, all right, based on how tall the adult mother is, can we make a prediction about how tall the adult daughter is? Okay, so we'll say x will be the height of the mother as an adult, and y will be height of the daughter as an adult. Okay. All right, and so do we expect there to be a relationship between x and y? Sure, we would expect there to be positive correlation, right? In general, if the mother is very tall, it is more likely that her children will be on the taller side, and if the mother is short, then the children have a higher chance of being short. But that's not the only thing that goes into determining how tall someone ends up being, right? There are lots of factors that go into determining how tall someone is. It could be height of the father. That's a factor. Okay, so there's different genetic things. Okay, so this is assuming biological relationships here. Other things, nutrition, other, whether or not, I don't know, other things, right? And nutrition's probably the biggest one, other than genetics. But lots of environmental factors. Did the person have lots of athletics as a child, or was there a certain medication or drug use, or all sorts of things can go into determining how tall someone ends up being. Okay, so let's say r between x and y is 0.6. Okay, then that means r squared ends up being 0.36. Okay, and so r squared tells us the amount of variation in y that is explained by x. So our explanation goes something like this. Okay, it would be like, there are many factors. This is many factors that determine or play a role in determining determining the height of an adult woman. Okay. Okay. One of which is the height of the mother. Okay, and what we're saying is that 36% of the height can be explained by the height of the mother. Okay, so we can say about 36%, and it's technically 36% of the variation, but basically 36% of, you know, an adult woman's height can be explained by the height of the mother. Okay, and that means, you know, the other 64%, that has to be explained by other things, environmental, other genetic, other factors that go into determining the height of somebody. Okay, and so in general, you know, and again, this is not a cause and effect relationship. Okay, it's not. We could, you know, flip it around and say, you know, what goes and determines the height of the mother, and the same thing would be true, right? Because if you switch x and y, correlation is still the same, and in our case, r squared would be the same, and we would say, you know, okay, there are many factors that determine or play a role in determining the height of an adult mother, and and this part sounds funny, but one of which is the height of the daughter. And it's not that it goes in and determines, but it's like, if we know the height of the daughter, we can explain some of the height of the mother, meaning that it's not that there's a cause and effect relationship between the daughter's height and the mother's height, but if we know this aspect about the daughter's height, we can explain part of the reason why, not the reason, but part of the high or low height of the mother. Okay, and so that is the r squared, and that's called the coefficient of determination. Okay, we'll end here for today, and we'll see you guys next week. Have a great weekend, everybody.